Welcome! In this series of short videos, we will look at topics common to both the PowerBasic console and Windows compilers. Today we will look at methods of searching large arrays. There will come a time in your development of applications when you need to deal with a great deal of data. One of the challenges of developing applications that are required to deal with volume data is where do you get the volume data when you're going to be developing and testing. Where this data may well be considered to be personal information, there may be restrictions on getting access to live production data. So there may well be a need to generate anonymized data. On the folder you can see before you, we have our application which we have yet to develop, and we have a folder called Generate Data. This is using code we've developed in previous applications. Within this folder, we have a number of files. Each of these files stores raw data. For example, cities. The cities has a selection of fictional cities. This is the seed data we're going to use to generate our random information. It also has first names, surnames, streets, job titles, and so on. You can use this approach to generate raw, anonymized data in any quantity. If we have a look at the code briefly that generates this information. In this application, we're setting a constant to the value of 50,000. This is a number of records of data that this application is going to generate. It's pulling in a library which we developed previously called random routines. And the output from this application is going to be a text file called mylargefile.txt. Everything is done within the generate file function. And within this function, we have a number of arrays to store the information held within those files we just looked at. We're going to generate a file which has a number of columns, starting with the email, through the first name and surname, and finishing up with blood group. As you can see from the format of the header, this is going to be a tab delimited file. Should you require a comma delimited file, just substitute a comma string or the tab constant. The next part in the function is to load each of these static files, these seed files, into its own array. And then once we have populated those arrays, we're going to do a for next loop for 1 to the maximum number of records, generating the information and pushing it out to the file. If we delete the mylargefile.txt that currently sits in the folder and we double click on the executable, it will launch and display a little pop-up box telling you how far it's got. As you can see, it's generating 50,000 records very quickly indeed. It took a mere 9 seconds to generate that information. So should you need more than 50,000, you merely have to adjust the constant to the value you wish. Now we can copy this mylarge file into our folder. So now that we've actually got a text file in here, let's have a quick look at it. As you can see, it contains all the information that we asked it to generate. So this 50,000 record file we're going to load into one large array inside our PowerBasic application. And then we're going to try 3 different methods of actually searching out data. We're going to consider the unique reference to our record to be the email address, which is the first column in our file. So let's now have a look at the code. So we will create a constant for the name of the file we wish to load in. And we will dimension an array into which we're going to load that data. And we're going to use one of the functions in one of our libraries, the file handling routines library, to load this file into our selected array. The read the file into an array function, which takes 2 parameters, the first being the path and name of the file, and the second the array into which you wish to load the data. Next, we're going to use the array sort command to sort the data into an array in ascending order, starting from row number 1. Row number 0 are the headers, so we'll leave them at the top of the array. So having got the data into the array, we're now going to try and search some data out of it. So I will create another constant at the beginning of our application called search string. This is the email address which we're going to be looking for within our file. As the array has been sorted alphabetically, in an ascending order, the user we're looking for, in this case Shannon, should be fairly far down the file. So this will give us a good test. So I'm going to create a function to search using a for next loop, and we'll call that function search for next, taking two parameters. The first being the array we want to search, and the second being the constant we're passing into that function for what we're looking for, in this case the email address of the user. Because we want to know how long it takes to actually search this, we need to have some kind of metric in here. And in order to get a good metric, I'm going to be using the ticks command. This is a command that measures the clock cycles of our CPU. We can do that quite easily by defining a variable as a quad, and we can start our count by using the ticks command, followed by the variable into which we want to put the value. And then once our function has completed, we'll use the ticksn command to finish off. And the value held within the qcount variable will be the number of CPU cycles which we can push out to our log to see how long that took. So now let's create the for next loop function. So there is the skeleton of our function taking its two parameters, a by reference array as a string and our search string, the email address we're looking for. So as this is going to be a simple for next loop, we merely have to use the for next command to go from 1 to the upper bounding of our array. As we don't know how big the array actually is, the ubound command is very useful as it will return the upper bounding of the array, the maximum number of records within it. Now we have to compare the information in the array with our search string. The long R element of the array will give us the data, which is the full data for that record, including the email address, the name, and so on. We're only interested in the left-hand part of it, which is just for the length of the email address. So we're using the len command to work out how long the search string is. So if our email address is 25 characters, then it's taking the left 25 characters and comparing it against the search string. Remembering when you're doing this kind of comparison, it's case dependent. But in this case, we know what we're looking for, so the case should match nicely. If in doubt, you can always use an L case or a U case to force it to upper and lower case for comparison purposes. If this returns true, then we know our entry has been found, and we can display some information in our log to say what we found and what row number. And at that point, we can exit the for next loop. So we're pushing out the first 50 characters to let's see what we found, and we're reporting on the row number using the format command to turn the numeric variable into a string we can display on the log. So let's try running that application now to see what we find. And we have indeed found the record we're looking for on row 45,625, and we took just over 18 million CPU cycles to find that entry. So this is our baseline for using a for next loop to search data out from the large array. So let's now look at a second way for searching out data from an array. As we did before, we're going to create a function to perform this, and we'll be using the ticks command again to count our clock cycles. So we're going to create a new function called search array scan, again passing just the two parameters, the array and the search string we're actually looking for. And after that's run, we will report on the number of CPU cycles used. So here is the skeleton of our new function, passing the two parameters and reporting in the log to say we're searching array scan. So we're going to be using the array scan command, which is inbuilt to PowerBasic. The first thing we need to tell array scan is the name of the array we wish to scan, in this case str data. As we don't know all the data that's in the record, we only want to look, in this case, at the first column, from the first character on that record for the length of the email address. The array scan command does have an option for scanning particular character positions, and that's what we're going to be using. That's the from command. We can go from 1 to the length of our search string. As our search string is an email address, it will vary in length. I'm folding the code line down to the following line so you can see it all on one line. So we're doing an array scan on the str data array from character positions 1 to the length of our email address. And we're looking for it to be equal to the parameter that's been passed in for our function, the search string variable. And should we find a value, we're passing that to the long R variable. If ArrayScan did not find anything, it would pass the value 0 back for that variable, as it's counting the first entry in the array as entry number 1. So in order to report this correctly, we need to report on long R -1. So let's try running the application now and see what these two scans will actually give us. So our first scan is giving us a value of 18 million CPU cycles, and the array scan is giving us a slightly shorter 15.6 million cycles. So at first glance, it would appear that the array scan is taking slightly less time to scan for our data. So next, we're going to be doing an indexed search. This is a third and final method of scanning this array. So let's go back to the code. With an index search, the first thing we'll need to do is to index the array. So this is going to be a slight bit overhead on the system. So we'll count this separately to see how long it takes to do an index on our 50,000 records. So again, we're using the ticks command to work out how many clock cycles we're going to be taking. I've set up a local variable called unique field to specify the field number we're interested in. In this case, it's the first field in the array. And we're setting the delimiter as being a tab. This will allow you to use delimiters other than tabs. Next, we're going to create an indexed array. The idea behind an indexed array is that we have a large number of records within this file. They're currently sorted alphabetically, so all the email addresses starting with A will appear at the beginning. So for any email address starting with the letter A, its start index will be row number 1. Its end index will be the last record which begins with A in the email address. The next letter would be B, and it will start from one more than that and go up to the last one of B. So we will have a start and an end index for each letter, A to Z. Should you require to have indexes on numbers, you'll need to use a slightly different method. But the idea being is if all the email addresses are equally distributed between letters, then you should be able to search only 1/26th of the entire array for the email address you're looking for. So in theory, it should be faster once the index has been created. So there is our index. I set up as 30 rows and 2 columns. And there is our new function, indexArray, which is taking a number of parameters. First being the array which we want to index, the second being the index itself, and the next two parameters are the unique field number and the delimiter in our records. And after that, we will end our clock counting and display the number of CPU cycles it's taken to generate this index. So let's now create the index array function. And there is the skeleton of our new function with its parameters. This function assumes that the array has already been sorted. It will need to be sorted prior to our indexing operation. And we're going to create a number of local variables. An index variable, a current variable, a slot number, which will be between 1 and 26, as this is the character that starts each email address, being A to Z. And finally, a unique ID variable. The unique ID is pulling out the value of the first column, based on the delimiter. In this scenario, this will be the email address, but it could quite as easily be the first name of the user or the surname of the user. Next, we're extracting from that unique ID the very first character. Should that value be blank, then we're skipping on to the next record. Next, we determine which slot in our indexed array this is actually going to be. And we're using the ASCII command to turn that first character into an ASCII value and then subtracting 96 from it. So for the letter A, this will give you the value 1. So this is the first slot in our indexed array. Next, we're looking to see whether the value of the index is actually changed from the previous one. And if so, we can save the details to our indexed array. We're using two constants here for the start and end, just for documentation purposes. And by the time we get to the very last value in our array, we can pick up that and mark its index end as being the upper bounding of the array itself. So we will create these two constants at the beginning of our code, index start and indexed end. So if we try running the application now, so we can see the value for the first two scans, and the number of CPU cycles for our indexing operation are almost 62 million. This is quite an overhead and larger than both of the original searches combined. However, you only have to index this array once. So let's go back to the code and make use of this index. And we're going to create another new function called searchIndexed. This is going to take 3 parameters. The 2 we've had for the previous functions, and the additional parameter is our index, the one we have just generated. And once that function is complete, we will then throw out the number of CPU cycles to our log. So let's go and create this final function. So here is the skeleton of our new function, taking in the 3 parameters: the data array, the search string, and our indexed array. So as with the previous for next loop, we're going to create a for next loop in here. As we did when we indexed the array, we're going to pick up the first character of our search string. This will be a letter between A and Z. And we're going to calculate which slot this is going to come into. And having determined that slot number, we can pull out from the indexed array the start and end row numbers, which we need to scan. Next, it's a straightforward matter of using a for next loop. But rather than scanning the whole array, we're only scanning for the start and end rows that we know that this particular email address should be sitting in. And once we find an entry, we can then throw our message out to the log to say which row number we found it on. So let's try running the application now to see what we get. So there we have our scans in place. The for next loop is taking almost 17 million CPU cycles. The array scan is now down to 5 million cycles. However, our indexed array scan is less than 1 million CPU cycles. However, it did have an overhead of 66 million CPU cycles to generate the index. So to answer the question, which of the 3 methods is the most efficient way of scanning large data, it depends on what your application is going to be doing and how often it's going to be doing it. If you're looking for only one record in a large array, then either the for next loop or the array scan is the way to go. If you'll be scanning this large array many times, then doing an index on the array is the easiest and fastest way of actually getting it to run quickly. We can quite easily see that by putting in a scan for 2 email addresses rather than 1. So let's create a second search string at the beginning of our code. So we're now looking for 2 email addresses. So we paste in a second call to the search for next, and the same for the array scan. And we'll add a second call into our index scan. So all 3 of these methods of searching out email addresses are going to be called twice. If we try running the application now, we can see from the first scan for 2 email addresses it was 34 million. For the array scan it was 10 million. And for the indexed array it was a mere 3.4 million. So the more times we scan this large array, the more efficient the index search appears to be. Hopefully this will give you food for thought in developing your applications where large data is involved. However, that's it for today. Thank you for watching.